Hi. Uh, Hi. We looked at we looked at quick sort in the last lecture, and in this lecture we are going to talk about heap sort. I'm actually going to take a diversion in this lecture and the next. Instead of using the slides from the Coursera course, I'm actually going to use slides from a different source, which makes the material very close to the Common Request algorithms textbook. Professor uses a different set of notations for the heap sort and the binary search tree, and I am very much tied to the algorithm introduction to algorithms by Common Request, so I went ahead and I'm just going to use those function names and the way things can be done. Okay, so let's look at heap sort. So a heap is a complete binary tree. What that means is that if you look at this particular tree, you will start filling it in this particular tree. As you can see that all leaves in this level, 1, 2, 3. So you can see level 3 are empty, and all levels before 3 are completely full. So that's the definition of complete binary tree. And typically what happens is that heaps, although you can represent them as a binary tree, what they typically get implemented are arrays, and we'll look into it as to how they can, how do you map this to this guy. So the idea is this is kind of the main, this is the main point. The parent, given a node I, the parent is ai by 2, the left child is a 2i plus 1, and the right is a 2i plus 1, right? So this is how you can come to this tree from this guy. So the property of a heap, there is also another interesting property. Okay, so we'll look into that. So that's how that's the definition. And once again, this is integer divide. What it means is it is not a floating point number. It's a real number. It's an integer number. Okay, so we looked at that. How do you implement this efficiently? Okay. So once again, something that I have not covered here. In case if you want to implement the heap using an array, you will have to deal with doubling the array, and when do you do that? And if we have already looked into it, that is still order n, it's 2 times n. So just keep that at the back of your mind. So this is the important property, the heapify property. The parent of I, the element at the parent of I, is greater than equal to all its children. Okay, what that means is if the parent is always bigger than the left child or the right child, doesn't really matter, but that's what is important. So value at the top of the, okay, so that is the most important thing, and the largest element is at the top of the heap. So these are the two most important things. Okay, so heap height, what is the height of n element heap? It is order log n, as you know, because it's a complete binary tree. And heapify is to maintain the heap property. What it means is, given a node I in the heap with children L and R and 2 subtrees L and R, the tree at I may violate the heap. Why? Because let's say something got inserted or deleted or something like that may happen, and then you have to you let the parent value float down, so the tree at I satisfy the heap property. Okay, so let's look at this. So let's look at a concrete example here that will make sense. So let's say, this is, in this particular case, here's 4, and clearly it is not right because 4 is less than the children here, right? So 14, 7, these are all children of 4 that are greater than 4. So what do? You want to swap 4 with the biggest of 7 or 14, because you want to make sure that once you swap it, this element is the largest. Once you do that, you want to again now run the heapify on 4 and the subtree where it is present now. In this case, you will again now have to swap it again, right? So that's the idea. Now you see it is at its right place, so as to speak. Okay. What is the running type of heapify? As you can see, it's still order log n. What is the worst case? Okay, answer is 2n plus 1. Okay, so this is in some more. I'm not going to go into details, but this is as to why it can be, why it's the order log n, and heapify is so what is the proof of that theorem. We can build a heap in bottom-up manner. Okay, so you can now build it. So let's say given any array and you want to build a heap on it, how much time will that take, right? So the basic idea is this. The first thing is that given an array n, all elements in the range a n plus 1 to n are heaps. Why? Because they are the leaves. So they are heaps. They satisfy the heapify property. So what you then want to do is you want to walk backwards from n by 2 to 1, calling heapify on each node. Correct? That's what you want to do. And how much time will that take? So let's look at. So this is what you're going to do. And this is any example. So this is what it means is this is any random array that you start with, and each heapify takes, so it's basically n log n, as you can imagine. That is what it takes. But is it a asymptotically tight bound? What it means is a tighter bound is order n, or order of n. And why this is actually important? Why it's actually order n and not order n log n? This is the important thing. Let's say heapify takes order h, where h is the height of the tree. H is equal to order log m, where m is the number of nodes in the subtree. As you can imagine, just imagine the tree. Let's look at this. Let's look at this tree here, right? Now you're calling heapify on these nodes. When you're calling heapify on these nodes, the length at that tree is not really order log n, where n is the total number of nodes in this entire tree. It is much less. In this case, it's actually 1. So what that means is you have to actually integrate where the height h goes from 1 to log n, and that's how the analysis needs to be done. And when you do that, once you just do the math here, and you can just take a look at the textbook, you will see it's actually order n. And what is heap sort? Now imagine what is the heap sort. Let's say if you actually want to do heap sort, how will you do that? You would, the maximum element is a1, so you take a1 or you swap that with an, and decrement heap size a. What that means is what's the maximum, and now you again call heapify on a1, correct? And you are continuously doing that, and then you sort the existing array, and this is what it boils down to. And once again, in this case, each of the heapify, it takes order n to build a heap. N minus 1 calls heapify. Each of them takes order log n. So as you can see, the total operation, the total time for heap sort is order n plus n minus 1 times order n log n, which is basically n log n. And this is where, but typical it's a nice algorithm, but in practice quicksort usually wins. We have already looked at quicksorts, but it's important for priority queues. What that means is that, and I think that we'll go to the professor's example and take a look as to where a place where this is really very valuable, and things that you can insert maximum, what's the maximum, what's the extract maximum, and things like that. Okay, so I'm back to professors, to the slides used by the lecture. I'm going to cover a couple of important things that I think were not very well represented in the earlier set of slides. So this is an insertion algorithm. When insert happens, you have to run heapify on the chain, on the parent chain, so as to speak. For example, when S gets inserted, you want to then look at the parent of H, then run heapify there, then again the parent, so on and so forth, till you no longer violate the heapify property. That's what you do there, and you continue doing that. Delete maximum we already know. We have known this to be equal to null to prevent loitering. So we have looked at swap and then delete. Java implementation, we're not going to worry about that. Okay, so heap sort, we already looked at heap sort. We know how that will work. So that's good as well. Now so here's the important thing, right? Heap, once again, we looked at the heap sort algorithm, n log n in place, maybe not stable. Okay, why is this important? Now look at an example here why you want to, and this is the, I'm sorry I was not able, I cannot show the animation, but the problem is there are multiple balls and each of these balls are moving, each of these particles are moving, and they bounce on the walls and they also bounce off each other, and you want to run a simulation trying to figure out that how do they, how does it behave, after an hour what happens and things like that. Turns out you can do it two ways. Either you can do a time-driven simulation, and if you don't have to worry about the bouncing of the particles within each other, you can just, after every, let's say, half a second or 500 millisecond, you can advance and then, draw the next position of the ball. And, this talks about how do you deal with physics. But now let's say you actually have to deal with the bouncing, right? That the particles bounce off each other, collide with each other. Now you can do time driven. What that means is that, okay, let's figure out a particular particle versus another, and then after every delta t figure out what's the, how do they behave. Now here are some problems with that. First is, do you want to make the delta t times too small? In that case, it will be very expensive. If it is too big, you may actually miss a collision, right? Because this guy might go here and this guy might already be here after some time delta t, so you'll actually miss them colliding, which is not good. And sometimes you might actually get into weird positions where these guys have already overlapped. What it means is they're already collided, and that will be imperfect. So the time division, we just spoke about it, excessive computation and many miss collisions. So ideally what you would like to do is event driven simulation. What that means is that just figure out when this is going to happen, and when this is going to happen, just do it. Okay, and we'll look into it as to how we can do that. The idea is this a couple of slides just explain the physics behind it, and how do you calculate when two particles collide with each other, how they are going to behave. We're just going to skip that. But here's something very interesting. What you would ideally do is have a class called as particle, and you would have these methods: time to hit a different particle, time to hit vertical ball, time to hit horizontal ball, and once this has actually been hit, how does it then, you tell it that, hey, you have already been hit by the vertical or the horizontal ball or the particle, and then take some necessary action. What it means is resolve collision. And how do you do it? You can imagine at a very high level what you will do is, you will start with all the n particles and then figure out which is the next collision that's going to take place. Okay, and we'll take a look at the code. Let's take, I guess this is the code. Okay, you find out what is the next collision that's going to take place. You take that collision off the heap and then update all the other nodes with the result of this collision. Does that make sense? What it means is, let's say there are two particles, A and B, and let's say there are all others that are around it. The moment they collide, now this might immediately bounce to another particle D, which was not the case. Hence D, which was going to, let's say, collide with E later, is now actually going to collide with B because of this collision between A and B. There are no particles here, I'm just kind of hand waving, but I hope you get the idea. And in that case, what you will do is, you will add these new collisions that are going to happen in this heap, and then you will do a reverse sort. What that means is the top of the heap will be the ones that's going to happen immediately, and then you will call heapify and say, oh, okay, this is what it's going to look like right now. Does that make sense? And there are lots of applications of something like that. Okay, that's pretty much for Heapsort. Thanks.